Hi, I'm Karl Gallagher. Welcome to Orbital Mechanics Without Math. Lots of science fiction stories involve stuff in orbits, but it's hard to know if they're getting it right. We have a whole bunch of kind of oral tradition of how orbits work. And the problem is the official classes for teaching orbital mechanics require calculus and have a lot of ugly math in them, but you really don't need all of that for the basics. So I want to share just some simple stuff about orbital mechanics so you can understand what's going on, write your own stories correctly if you're a writer, and as a reader, know if somebody's getting it right. Is this something really weird because it really works this way, or does it seem wrong because it is? Just to give you my own background, I did do the calculus version of orbital mechanics. One of my professors, Richard Batten, had actually been one of the people developing the guidance system for Apollo. So we were very much digging into the details of it. I went ahead and used that orbital mechanics experience operating weather satellites for the Air Force. You see the Defense Meteorological Satellite Program bird here on the left. And then I went into industry, was working on launch vehicles, various types of satellites, including another weather satellite, NPOS, which unfortunately in the way of many development programs wound up not actually flying, though we did get a prototype into space. So it did better than some. So a lot of the examples I'll be giving you is focused on Earth orbits because that's what most of my experience has been. When you think about orbits, a lot of how they work was worked out by Isaac Newton. And Newton came up with a lovely metaphor for how an orbit works, Newton's cannon. If you fire a cannon, the cannonball goes a certain distance and hits the ground. If you fire it at the same angle even faster, it'll go farther before hitting the ground. So in theory, if you fire it fast enough, the cannonball will go all the way around the Earth. And what Newton worked out is that firing it faster doesn't make it go 1.5 times around before hitting the ground. If you're going fast enough, and this is ignoring air drag and similar complexities, it will go into a loop and keep going around and around the Earth. And that's what an orbit is. If you're going fast enough, you keep going around. Now, if you fire it even faster than that, it'll go into a higher loop, going even farther away from the Earth. And if you fire it extremely fast, it'll escape and just go away from the Earth and never come back. So what's going on physically with this? Well, what's happening is we're balancing the forces on the satellite. This little kid is doing a classic science experiment. He's not feeling very confident about it, but this actually does work. You can take a bucket or a heavy object and swing it around your head on a rope, and it will stay going in a circle because the force you're exerting with the rope is actually balancing the centrifugal force on the object in a rotating reference frame, or an inertial frame, if we have any physicists here. We're getting an acceleration on it that pulls it into a circular force. So what's happening here is that the centrifugal force of the bucket balances the force on the leash, pulling it toward the center. In space, what we have is gravity acting as that leash. So gravity pulls on the satellite, but the satellite is moving so fast that the centrifugal force balances out the gravitational force if you're going the right speed. If you're going slower, the satellite will be pulled in by gravity. If you're going faster, the satellite will move away from the gravitational force. But if you match it exactly right, you are in a circular orbit and will just keep going in that circle forever. So circular orbits, how fast you're going depends on how high you are. So we see here a couple of orbits around the Earth. The yellow one is a 2-hour orbit. It's in close. Gravity's pulling on it hard, so the satellite has to go very fast to stay up in the circular orbit. Then we have a 24-hour orbit as the blue circle, which has some interesting uses we'll come back to later. And that, at that distance, gravity is much weaker, so the satellite doesn't move nearly as fast. So the 24-hour satellite is moving about a third of the speed that the low orbit satellite is in. Now, if you're not in an exact circle, you're in an ellipse. And yeah, it's a geometric thing, but you can actually define an ellipse without doing any math. Just go ahead and take a couple of nails, tie some string to them, and you put a pencil into that loop of string and draw it out, and the shape it makes is an ellipse, which is pretty much that any point on the ellipse always has the distance to the two nails, which each nail is what's called a focus. That adds up to the same. So you can skip the math on it, and the geometry of it is just that you have, this loop of string and draw out your ellipse. If the two nails are moved together for a single focus, you get yourself a circle. If you move the nails infinitely far apart, it's called a parabola. So let's look at some actual elliptical orbits. So here we have a bunch of satellites going around Earth. They all have the same perigee, which is the same point closest to Earth. But their apogees are different. The apogee is the point farthest from Earth. So the red orbit here is circular, which is an ellipse with an eccentricity of 0. One of the mathematical ways of defining it. If you increase the eccentricity, then you get these ellipses with 0.2, 0.4, 0.6, 0.8 eccentricity. And if it becomes an eccentricity of 1, is again a parabola where the focus is infinitely far apart. Now, if you think about where the nails are in the diagram I showed you, the center of the Earth is the position of one nail. That is the focus. And the other position is what's called the empty focus. So that's kind of a mathematical abstraction, but it really is, it's part of the geometry of how you work it out. Now, all these different satellites, in perigee, they're going through the same point, but each one is a little bit faster according to which ellipse it's in. So the faster it's going, the higher its apogee is going to be. The speed of the satellite also changes as it goes through the ellipse. So it's fast at perigee, and then it slows down at apogee. You can think of it as apogee being uphill, so you slow down going uphill, and then like a bicycle, you pick up speed again going downhill. Now, Kepler actually worked out a bunch of the math of this. Kepler's second law doesn't actually need math. What it is saying, if you look at the line between the satellite and Earth, or in Kepler's case, a planet and the sun, because he figured this out watching the planets, the line that they sweep out in a certain amount of time will always be the same area. So when it's close to perigee, or perihelion in the case of the sun, it's short, so you have this wide chunk that sweeps it out in constant area. Out on the other side, you're sweeping out a very narrow, long and narrow piece, but the area is the same, so it goes through here very slowly. So you can see the more eccentric your ellipse is, the greater the ratio is going to be between the apogee velocity and the perigee velocity. And if you look at this in-between case, yeah, the speed is in between, and it's going to be symmetrical. So going uphill, your velocity is changing the same rate as it does going downhill. Now, an example of how that'll give you different behaviors, these two orbits are both 12-hour orbits. You have the blue orbit going around Earth in a circle. And then we have the magenta orbit, which is 12 hours in a very elliptical fashion. And so, as you can infer from the previous diagrams, the magenta satellite is going to spend most of its time at a higher altitude than the circular one, even though it has a perigee that's, very close to the Earth. It just goes through here blindingly fast and then slows down and just kind of ambles along at apogee. And there's some interesting things you can do with that we'll discuss later. Now, the diagrams I've been showing you have all been showing orbits in the equatorial plane, all over the Earth's equator. And you can put a satellite there. The only problem you have is it's difficult to launch them into there unless your launch site is on the equator. If you're launching out of Florida, that's going to put you about 28-30 degrees inclination relative to the equator. Inclination is the term for the angle your orbit makes with the equator. The Russians have an even worse time because their launch sites are farther north, so they wind up in this white orbit, passing over it. Now that has some utility because if you're wanting to see the whole world in the equatorial orbit, you only get to see the equator. If you really want to see the whole world, you can put your satellite into a 90-degree orbit, and so you go from the North Pole to the South Pole, and the entire world turns underneath your orbit, and you get to see that all. Now, that's not the only geometry you have to think about when you're positioning an orbit. There's what we call the ascending node. So we've got, here we have the yellow equatorial orbit for reference, and we've got 4 different orbits crossing over the North Pole. And on the right side, you see the North Pole view of it. So here these orbits are crossing at different angles. The red and the blue ones are actually a 90-degree angle to each other. So even though they have the same inclination, they're at the same altitude, they are very different orbits. And this is what we refer to as the ascending node because we measure that where the satellite crosses the equator going north. That's the technical term for it. And this is something you have to worry about for a lot of missions, particularly if you're trying to meet up with another satellite. So say we have a Crew Dragon going to the International Space Station. Does it matter if this Crew Dragon launches an hour early or an hour late? Well, let's look at the orbits we get from that. You can see that the ascending node of these orbits, even though they're the same inclination as ISS, they have a huge separation at the equator. Now, you might think, well, okay, but you can still rendezvous because the orbits intersect, right? And well, yeah, let's look here over the Atlantic, and we can say, okay, even if you're early or late, the orbits intersect, but let's take a closer look at that intersection. Okay, so here we have the ISS and one of the mistimed Crew Dragons, and that's about a 12-degree difference. And the problem with that is these guys are going along at over 7 kilometers per second, nearly 5 miles per second. And so the relative motion of them as they pass each other in this intersection is faster than a bullet fired from an M16. So you do not want to try and dock with that kind of relative motion. It is very expensive to do orbital plane changes like that Really, if you find yourself in a situation like that, you will frequently be better off deorbiting and launching again. This is also why orbital debris can be scary, because that can be a piece of debris can be in any orbit with any inclination, any ascending node. And if it intersects your orbit, it's probably at a significant angle, which means it's going to be even faster than that rifle bullet. So that is a real worry that folks in space have. Now, changing altitude is a lot easier than trying to change your orbital inclination. So we see some folks, they're in a yellow circular orbit at low altitude, and they want to move to a somewhat higher altitude with the blue circular orbit. Now, you can't just switch from one circular orbit to another. You know, any maneuver you make puts you into an orbit that includes the point where you make the maneuver. So you need to have a transfer orbit that connects one to the other. So that's this red elliptical orbit, where the perigee of the elliptical orbit is your starting orbit and the apogee is the destination. So what you do is you would go ahead and do a slight burn on your thrusters in the circular orbit, and that kicks you up into the ellipse. And then once you get to apogee, you would speed up again to circularize your orbit, because your apogee is moving faster than the circular orbit that, you know, the apogee is slower than the circular orbit of the speed of your destination. Now, one of the things you have to worry about if, say, you're doing something like transferring some astronauts to the space station is you don't just want to be on the circle, you want to be at the exact same place on the circle. And so sometimes what you'll need to do is wait a few orbits before you do your maneuver, because in the yellow orbit, you're going around faster, so that as you've completed a full circle in the yellow orbit, the space station in the blue orbit has only done part of a circle, so you're changing your relative position. So if you happen to be offset from where the space station is, and that'll frequently happen because the launch window for getting into the right orbit plane is not going to match with the launch window to line up for an exact rendezvous. You know, what you do is you'd spend several orbits in the circular orbit and possibly even go into the transfer orbit and then spend several orbits waiting there, because that has a slightly different period and would give you a different increment on each orbit before you go ahead and do your circularization. And so when you see the Crew Dragon launch and then they sit in orbit for a day or two before actually rendezvousing with the space station, that's what's happening. They're waiting to get their position matched up exactly. Now, another frequent kind of orbit transfer is going to GEO, where the communications satellites are. And this is an orbit transfer that has a plane change. So what we see here is somebody launched their satellite out of Florida, got themselves into a 28-degree inclined orbit. And then when they're crossing the equator, they boost up to what's called GTO, an eccentric orbit that goes from low above the Earth all the way out to the altitude of the 24-hour orbit where the communication satellites are. And so you're not trying to do a significant inclination change here at perigee, because that would be expensive. But when you get out to apogee, you're moving so much slower that it actually is not that big an issue to do an inclination change. So they will circularize to the 24-hour orbit and do their inclination change to make it 0-degree inclination over the equator at the same time. Now, one of the things you have to worry about when you are doing an orbital maneuver, and this is more a spacecraft design than an orbital mechanics issue, but it's something that comes up a lot, so I wanted to mention it, is for real spacecraft, you have to have your engines on the center line. The Enterprise, no, Star Trek, they have warp engines instead of rocket engines, but it's a frequent example of science fiction spacecraft having their engines off-center in some dramatically visible position. And yeah, it's good art. It has nice visual effects. But if you are actually trying to design a spacecraft that will work, you need to be like the Apollo Lunar Excursion Module, where you have your rocket engine right on the center line of the ship. And the reason for that is you need to keep track of the center of gravity of your vehicle, which is more or less where the center of the ship, where the mass is concentrated. Because if you don't have your thrust line lined up with that, here's Mark Watney in The Martian trying to play Iron Man. So what would actually physically happen if Watney tried that? Well, you see what the force vector is here. The air jetting from his cut glove. And you see the vector line here is going parallel to his spine, but offset quite a bit. So this would essentially be torquing him on this lever arm, because you'd get torque around the center of gravity. So what would happen is Watney would wind up getting spun up, and the thrust would be spread in a full circle. He would not actually accelerate toward the people trying to rescue him. He would just wind up hopelessly spinning, unable to regain control of himself, and out of air. So not a good idea. Even if it's an intentional rocket engine, you don't want to have it off to the side like this, because it will spin you. Now, airplanes can put their engines off the center line because they have tail fins to balance that torque. Ships can do it because they have keels to balance the torque. Spacecraft don't have anything, unless they're going to use their attitude jets to try and counter the torque. And you generally can't afford that. You just need to go ahead and put your thrust aimed at the center of gravity. And another example you can see of that in practice, if you've been watching the videos of SpaceX's Starship prototype flights, they have a cluster of 3 engines. And the 3 engines are centered so that their combined thrust goes through the center line of the ship. But when they shut one down, you will see that the remaining 1 or 2 engines will promptly tilt to make sure that their thrust is going through the center of gravity. Because, even with the fins on that ship, it's going to get spun if the rockets are not aiming for the center of gravity. Now, they'll do that on purpose as part of doing the flip maneuver. But if you're not doing it on purpose, you can get yourself in a lot of trouble that way. Now, something that's been in the news recently was the re-entry of a Chinese launch stage, because they launched, as part of launching their space station, the booster went high enough that it went into orbit, but it was uncontrolled. And so wound up re-entering in a random location, which had some people kind of worried, until it actually wound up in the Indian Ocean, because Earth is mostly ocean. So the odds are with us for random re-entries. Now, the way drag works on stuff like that is if you have a wide orbit, say you have a 24-hour circular orbit, and then you lower your perigee down to put yourself into this green elliptical orbit, lower yourself down to where you can be brushing into the atmosphere. The drag that you take on each pass doesn't change your perigee much. What it's going to do is slow you down, and that will lower your apogee. So, if you get yourself into this aerobraking zone where you don't instantly crash into the earth, but you are getting a fair amount of drag, what that's going to do is circularize your orbit at a lower altitude. So after each pass, that's going to lower your apogee down until you're in this low circular orbit. And there are spacecraft that will do that on purpose. Mars missions, for example, where they will slow down by aerobraking and then circularize their orbit. So you could, for example, go into the, keep going until your apogee is lowered to the green orbit here, and then circularize, and that would be a lot cheaper than trying to go directly into a circular orbit. One of the problems with trying to do that sort of maneuver is atmosphere has a lot of variation. It's not just the weather, the jet stream and such changing the density of the atmosphere, but at the altitude satellites deal with, what you'll have is solar weather changing the heating of the atmosphere, and that'll make it fluctuate a lot. So it is very hard to predict exactly how much drag you're going to get from a particular pass. And so again, with that Chinese booster, you wound up having uncertainty on when it would re-enter of plus or minus 2 hours. And when the thing takes 90 minutes to go around the entire planet, a 2-hour uncertainty window means it could land just about anywhere. So it is unfortunately a fuzzy business. Now, one of the things I'd mentioned earlier is a geostationary orbit. This is an orbit that takes 24 hours, so it turns with the Earth. So if you have your satellite completely circular at 0-degree inclination, your satellite will stay over a single spot on the equator, and from the viewpoint of someone on the Earth, it doesn't move at all as it makes its daily orbit. And anyone who has a satellite dish is taking advantage of that, because you can simply set up your antenna, go ahead and line it up, and as long as the satellite is kept in the right position, you don't have to worry about it at all. You'll just have a solid connection. Now, not every geosatellite is geostationary, which is that term. Some are inclined, but unfortunately, this particularly disappoints a lot of generals. You can have a geostationary satellite that is inclined relative to the equator, but it's going to spend as much time north of the equator as it does south of the equator. So you cannot station a satellite over Moscow. This was a running gag when I was in Space Command, because there'd always be a general from some non-space outfit who wanted to do that and was very disappointed we could not oblige them. If you just take a perfectly circular one, incline it a bit, you'll get a kind of figure-8 position traced out on the ground. You can also make your orbit slightly eccentric, and do various other ground tracks, and some satellites will wind up doing a bit of wiggling on purpose to minimize the amount of station keeping they do. A geostationary satellite, sure, by Newton's laws, it would just remain in that position. Unfortunately, there's more than just the satellite and the Earth. There's perturbations from the sun's gravity, there's perturbations from the moon's gravity, and there's also some interesting things that the Earth is sufficiently irregular that the irregularities of the Earth's shape will pull satellites in some directions or another. So if you, even if you manage to cancel out the sun's effects, the Earth's gravitational variations will wind up pulling a satellite east or west until it winds up collecting over some of the high dense anomalies over the Earth. Now, one of the problems with a geostationary satellite is it's great for watching the equator, it's great for seeing from the middle latitudes, but when you get into the high latitudes, the polar regions, it can be hard to see it because it's so close to the horizon that trees will obstruct it. You'll have a lot of atmosphere obstructing it, and if you get far enough north, it'll actually be below the horizon. You can't use it at all. You know, not as big a problem for the US, but the Russians have a huge problem with that because they are so far north. So they came up with, let me try and get this right, the Molniya orbit. Molniya is, I believe, lightning in Russia. And this is that elliptical 12-hour orbit I showed you before. And so it will go ahead and just have a quick perigee pass in the southern hemisphere and then go up and stay visible for hours at a time from the northern regions. It's not as nice as a geostationary satellite. You still have to have a tracking antenna that can follow the satellite, but it will stay in view. And they would generally have 2 or 3 of these satellites so that, you know, there's one to cover the others while it's doing its southern pass, so that it would switch among the satellites in the constellation. Now you notice this isn't a precisely 90 degrees over the pole inclination. And that's because with the Earth's irregularities, the bulge at the equator, there's sort of a pear shape as well, if you analyze closely enough, and some of the just random irregularities. You know, one of the things that will happen is orbits get perturbed, and it will change the location of an orbit's perigee. And, you know, if you analyze those factors, you can actually figure out where to put the orbit to cancel out those perturbations. So the Molniya orbits are set up so that their perigee will stay constant. They'll still have perturbations changing their ascending node, so the ascending node drifts relative to the Earth, but that doesn't change the mission. As long as you know where the satellite is, you can communicate with it, and as long as the perigee stays over the northern hemisphere, it'll stay visible for you. Another thing that people will do to take advantage of those gravitational irregularities is figure out what orbit will get the ascending node to be perturbed so much that the ascending node does a full circle in a year. And turns out, you know, if you have something about 500 kilometers altitude, about 98 degrees inclined, so it's actually a bit more than 90 degrees, you know, you launch it a little bit backwards, you can achieve this full circle in a year, and that means the plane of your orbit is staying constant relative to the sun. And there's a couple of interesting features with that. One is the example I've got here is a satellite that is staying in sunlight continuously. Most satellites are going into shadow behind the Earth, you know, at once every orbit. But this one is staying constantly over the sunrise-sunset line, the terminator of the Earth, and that keeps its solar panels constantly illuminated. Depending on your exact orbit, you might get some shade during the solstices. But usually what a sun-synchronous orbit is used for is Earth observation, because however you're oriented relative to the sun, you will have a fairly constant shadow angle on the ground as you're taking your pictures. And this was a big deal for the weather satellites I worked on. If you put it in a noon midnight orbit, all of your daylight pictures would have minimum shadows, or you could have a light morning one where you would have a consistent 30-degree shadow or 45-degree shadow. And that's very useful because it lets you not have to worry about, are the forests coming into leaf? Is something changing? Are we having differences in our imagery because it's a morning picture versus an afternoon picture? It's consistent, and that way the differences you're looking for are just the clouds moving overhead, letting the weather people do their jobs. Let's see. Another question that keeps coming up is, for some reason, people really like the thought of dropping something into the sun. Or in the case of a satellite, can we just drop it into the ocean? And well, if you're not already in a very low orbit that's about to go in, you're probably actually better off sending your satellite away than trying to bring it in. And so the bar graph here is the amount of velocity change that you would need to take a geostationary satellite and drop it into the ocean versus boosting up that geostationary satellite and sending it into an escape orbit from the Earth, never to be seen again. And you've got the same ratio if you want to take something from the Earth and drop it into the sun or have it escape the solar system. It's a lot cheaper to just send something away forever than to try and get it to the bottom of the gravity well. Just because you're already going so fast being in the orbit you're in, that trying to get rid of all of that velocity is a lot of work compared to just speeding up a bit to leave. Now, for geostationary satellites, this is actually done in practice. They don't send them to escape. That's a little more expensive than but what they'll do is boost it up a bit to what's called a graveyard orbit, where it'll be high enough that it's not going to get in the way of the replacement geostationary satellites. And they do try to avoid letting junk accumulate in the geostationary belt, because that's such a precious resource that they don't want to clutter it up with junk and endanger operational satellites. Now, something that is falling toward the sun is comets. And we see here a diagram of the orbit of Halley's Comet. And that's a really eccentric orbit, because you can see it's falling in almost toward the sun with the inner planets. And then it goes all the way out to the orbit of Pluto. A lot of comets are in long eccentric orbits like that. They're not always as regular as Halley's Comet, because if one of them flies close to Jupiter or Saturn, that'll perturb the orbit. And so it will wind up in a different long ellipse and not coming so regularly. If you have something falling in all the way from the Oort cloud, it may look like a parabola. If it's something where we're not going to see it again in recorded history, it's effectively parabolic. It might technically be an ellipse, but it's still just coming through once. Now, one stuff we know are absolutely only coming through once are hyperbolic orbits. Our example here is the interstellar visitor, Oumuamua, which is probably an asteroid or comet of some kind, maybe an alien spaceship. I would put my money on an asteroid. Unfortunately, we didn't see it in time to get to a probe to it, which would have been awesome, because these things, a hyperbolic orbit is going through fast. And pretty much this is what an escape trajectory looks like. It is a very fast orbit. The faster it is, the straighter it is. If you have an interplanetary spacecraft doing a flyby of a planet, now from the planet's point of view, that's a hyperbolic orbit. Let's see. Something that comes up in a lot of science fiction stories is Lagrange points. I am always tempted to call it a Lagrange point because Isaac Asimov did a great film Home on Lagrange about space colonies. But the actual scientist who did the math on this was a French guy called Lagrange. And this is looking at some things in, an orbiting system. If you have, the Earth and the Moon, or the Sun and Earth, or the Sun and Jupiter, you will have some points relative to those two where something can have a slightly different orbit with stability. So if we have the Earth and Moon, there is a point between them, L1, where in the rotating reference frame, their gravities just balance out and something can move along at the speed of the Moon's orbit despite being at a different altitude relative to Earth. And so this can be a very useful place to put a communications relay or something like that. On the opposite side of the Moon, you have the L2 point. And what we have here is the combined gravities of the Earth and Moon being balanced out by centrifugal force in the rotating reference frame. And so this lets you station something on the opposite side of the Moon, which we have actually gotten some use from, because if you don't want to deal with the noise of the Earth, for example, all of the thermal radiation the Earth emits, you could put the Herschel Space Telescope there, which did infrared observations, and it was at L2 to not have to put up with the Earth's emissions. On the opposite side of the Earth, we have the L3 point. I'm not aware of any actual missions people have done using the L3 point, but it's there if anybody ever needs it. One of the things about the L1, L2, and L3 points is they are unstable. If you put something in there and it gets perturbed away by, say, the Sun or Jupiter's gravity, or just something springs a leak and you have a vent pushing you away, that'll get you, you'll have to do some station keeping to maneuver yourselves back. And so a lot of the satellites using that will do what's called a halo orbit, where they just actively maneuver around the point. What makes the L4 and the L5 points interesting is that they are dynamically stable. Something that gets there will be pushed back by the combined gravities. And so it'll wobble around a bit, but it'll stay there. And this is a phenomenon that's been seen with the Sun and Jupiter, in that the L4 and L5 points have actually accumulated a bunch of asteroids, which were named after heroes of the Trojan War. And so these are also called Trojan points. And that stability has made folks want to put space colonies there. Let's see, space elevators are a very fun concept. We have not figured out what we can make a cable out of that we can actually build yet. But the idea is, just like that kid spinning the bucket, if you have a long cable and a weight at the end of it, the Earth will spin it like that bucket and the cable will be held taut, and you can put an elevator on that and it'll go up. Main thing I'd want you to remember here is, the counterweight has to be higher than geostationary altitude. Otherwise, it won't have enough centrifugal force and will fall down. I've seen some good authors make that mistake, unfortunately. Counterweight has to be way higher, and the more tension you have in the cable, the more cargo you can run up with your elevator cars. One nice thing is that at geostationary altitude, there's no force exerted, so you could build a space station there, and it's not going to bother your system at all. Navigation tools. People go, well, NASA needs all these fancy computers, but Pulp Fiction heroes just have a sextant and a slide rule. That's not realistic. Well, you know, NASA needs a lot of precision because it's trying to strain the ultimate capabilities of their system. A pulp hero in a torch ship can go ahead and have some low precision tools because if he's off by 10%, he can just steer, get there. Think about how you would drive your car with a full tank of gas compared to if you're trying to get there when you're going to run out of fuel and coast into the gas station on momentum. You know, which scenario are you more worried about making a wrong turn in? And if you want to do some orbit work on your own, the illustrations I made here were done with Satellite Toolkit. This is a professional analysis program. It's expensive for industrial use, but they are actually pretty good about giving free sample licenses, and will sometimes give out permanent licenses for educational purposes and so forth. A very popular orbit program is Kerbal Space Program. It's more focused on spacecraft design, but it does do real orbit analysis. And there's a large user community out there for Kerbal Space Program who can help you with stuff you're trying to do in it. And there is another program I have not used, but I've seen people do orbit stuff with it called Universe Sandbox, which will not just analyze orbits, but you can make your own planets. So that's the basics of orbital mechanics. I will be hanging around in the chat channel if you have any questions. Thank you very much for your time and interest.